Hello everyone, welcome to topic 8.2 pH and pOH of strong acids and bases. By the end of this, you should be able to calculate the pH and pOH based on the concentrations of all species in a solution of a strong acid or a strong base. And so we're going to look at these three equations in application in this section. So for strong acids, you will recall that the 6 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. Strong acids are strong electrolytes, and so when they are added to water, they dissociate completely into their ions to form an aqueous solution. Electrolytes can conduct electricity when they are in solution. For monoprotic strong acids, so that means that they only give off or donate 1 proton, the concentration of the acid is equal to the concentration or molarity of the hydroniums as shown in the equation here. For sulfuric acid, only the first hydrogen dissociates completely as shown in this equation. However, in a reaction with a base, both hydrogen ions will react. So the second hydrogen is treated as a weak acid, and it's a different process to calculate that concentration. Strong bases are soluble hydroxides. They dissociate completely in water and are therefore strong electrolytes. They are group 1 alkali metal hydroxides and group 2 alkaline earth metal hydroxides, which only include calcium, strontium, and barium. Beryllium and magnesium are not included as strong bases because their hydroxides have limited solubility in water. Okay, so they are not strong bases. For strong bases, you can calculate the concentration of the hydroxide using the initial concentration or molarity and the ratio of the hydroxide ions in the formula. For calculations of pH, you can use the negative log of the hydronium ion concentration as shown in the example here. For calculations of pOH, you can find it by taking the negative log of the hydroxide ion concentrations as shown in the example. The relationship between pH and pOH, they always sum to 14 at 25 degrees Celsius because they are derived from Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, where Kw is 1.0 times 10 to the negative 14 at 25 degrees Celsius. So we can say that pH plus pOH is 14. In this example, we see how we can use that equation to figure out the pH given the hydroxide ion concentration. The more concentrated an acid is, the lower the pH will be. Oops, my apologies. The more concentrated the base is, the lower the pH will be. So a more concentrated base will have a higher pH. Acids have pH values that are lower than 7, while bases have pH values that are greater than 7. So let's look at how we can use these equations and the concept of acid and base on this scale in an example problem. Okay, so find the pH of a mixture of 10 milliliters of 0.001 molar solution of potassium hydroxide and 10 milliliters of distilled water. Well, since we're adding water to the solution, we know we're going to have a new volume that is the combination of the two. So this is technically a dilution equation. So we need to use the dilution equation to find the new concentration of potassium hydroxide, and then we can determine the pH of that solution. So the dilution equation is M1V1 equals M2V2. Okay, substituting in for volume 1, molarity 1, and volume 2, we can solve for the molarity 2, which will allow us to calculate the pH eventually. So substituting in what we know, we don't have to convert the volume quantities, 2 liters, because the 2 volumes are in the same unit, so it technically cancels out. And you are left with a molarity of 0.000500 molar potassium hydroxide solution. So we know that the pOH is equal to the negative log of that concentration. And these are all base 10 logs, which is why this scale changes numerically 1 by 1 for every value or factor of 10 that the concentration changes. So solving this, we end up with a pOH of 3.301. Okay, and we also know that pH plus pOH is 14, so we can say that the pH is equal to 14 minus the pOH, which we said was 3.301, so we end up with a pH equal to 10.699. Okay, we're going to apply the same principle to the we do in question 10, or in this next one, where we have 100 milliliters of sodium hydroxide solution with a pH of 12, and how do we get that to a pH of 11? So, looking at this, we know we have a hydroxide ion concentration that is at, so this is our initial where we're currently at, and if we go inverse, we know that this is 14 minus 12, so we know we currently have a hydroxide ion concentration of 1 times 10 to the negative 2 molar, or 0.01. And then here, we have a hydroxide ion concentration. For our final one, we want to get it to pH 11, or pOH 11, no, pH 11, so we need to figure out, my apologies. So the reason why we do 14 minus 12 or 14 minus 11 is when we look at pOH, which to get the hydroxide ion concentration, you use pOH, 10 to the negative pOH, that is 14 minus the pH, and since we have our current pH and our desired pH, we have to convert those to pOH before we can determine the hydroxide ion concentration that we start with and that we want to find. Okay, so for this is also another dilution equation because we want to go weaker. So we want to dilute this down. So our M1 is going to be our initial concentration. Our M2 is going to be our final concentration. And our V1 is going to be our initial volume. We want to figure out what our final volume needs to be to get to this pH or adjust the concentration of the solution to this. Okay, so M1 V1 is equal to M2 V2. So if we substitute in for the values we know, and solve for V2, you should end up with 1,000 milliliters, or if you wanted to change that, that would be 1 liter. So you would dilute original solution (1,000 milliliters) or 1 liter. And just to be specific, we would do this with distilled water. Okay, so using these concepts in the equations given above and on your equation sheet, complete the you do, check your work, and thank you for tuning in.